Hello everyone. In this video and next 6 or 7 videos, we will be talking about the discrete time system analysis using the Z transform. So let's look at the outline of this chapter. So in this video, we will talk about the Z transform. We will define what is the Z transform, how does it relate to the signal in the time domain. For example, if you have a signal x of n and we do the Z transform to get x of z, what does x of z tell us about the signal x of n? It tells us the frequency content. So we're going to learn how do we move from x of n to x of z. Then the next topic will be the inverse Z transform. Now let's say we processed x of z and to extract certain information. Now we want to convert it back to a signal in the time domain. So that will be x of n. Now we will do the inverse Z transform. The next topic will be the properties of the Z transform. We're going to learn about time shifting, scaling, converting difference equation to the Z domain. And this property will help us to understand more about the signal and use some of these property for system analysis. For example, in this topic, we will use the difference equations property. So the Z transform solution of linear difference equation. So now we have this difference equation that describe a system. How do we solve this difference equation? Means find y of n for any specific value x of n. And we did this in the time domain. Now we will learn how to do it in the Z domain using Z transform. The next topic will be block diagram and system realization. Here now I gave you a system described by this transfer function h of z, something like this, for example. And we want to build this system. This system could be filter, amplifier, do certain signal processing, extract certain information from a discrete signals. So how do we build this system? So that will be the block diagram and system realization. The next topic, we will move to the frequency response of discrete time system. So now we're gonna learn how do we get from the transfer function h of z, the frequency response of the system, h of omega. And how does this system respond to a sinusoidal of different digital frequency? And from this knowledge, we're going to move to this topic, which is system design by poles and zeros placement. So now we will learn the effect of the poles here and the zeros here on determining the behavior of the system. Okay, so let's move on to the topic of this video, which is the Z transform. Before we start defining what is the Z transform, let's learn about what is the Z variable and how does it play a role in building a signal. So we're gonna learn from these basic signals. I can make any complex signals as a linear sum of these basic signal and see what is Z in these basic signals. So for example, if I define a signal x of n to be z to the power of n. Now z can have any value. It can be a real or it can be a complex. That means a complex, it has a magnitude and phase, but in this case we will call the phase a frequency. So for example, z can be minus 0.8. So now this signal will be minus 0.8 to the power of n. And for different value of n, it will just decay and alternate between positive values and negative values. And z, if I plot it in this z plane, it's just this vector. This is the unit circle. Now let's look here. When z is 0.8, it is this vector. So now I can construct this signal, x of n equal 0.8 to the power of n. So this is, again, because this is less than 1, it's a decay. And the decay rate is determined by this value 0.8. Now let's look at this signal when z is minus 1.2. So that's here. In this case, this will be minus 1.2 to the power of n. Now this is larger than 1, so it will be exponentially growing with alternating between positive and negative values. If it's here, if z is 1.2, this will be just exponential growing signal. Now if z is on the unit circle and it's minus 1, so now this will always have magnitude 1, but it will be alternating between positive values and negative values. So this will be minus 1 and this will be positive 1. And this one here, it's 1, that will be this one. Now z1, which is this one, and z2 is this one. So if I draw z1 as a vector, it will be this. Let me enlarge this screen. So z1 looks like this. It has a magnitude, which is this vector length, 0.8, and it has angle. And I can call this angle omega, which is pi over 4. In previous, we used to call it phase, but here we will call it digital frequency. When omega is pi over 4, I can write it as 2 pi times 1 over 8. Now you can think of this as the digital frequency, and it means you will have 1 cycle per 8 samples. Like the continuous frequency, we call it 8 cycles per second. Here, it is 1 cycle per 8 samples. Now, if you have a complex Z1, then you will need to have its conjugate for xn to be a real signal, which is this one. And this will be minus omega, minus pi over 4. So this signal then will be x of n equal 0.8 n plus 0.8 n. And I can do some algebraic and complex manipulation, and this will be 0.8 n times 2 cosine pi over 4 n. So 0.8 to the power of n, that will determine the decay rate. How fast is it decaying? Pi over 4, that will determine the oscillation rate. How many cycles per samples? In this case, it will be 1 sample, 2, 3, 4, 5, 6, 7, 8. That's the peak. So then there is 1 cycle per 8 samples from peak to peak. Now if Z1 is 1.2, EJ pi over 4, that will be this one. So it's outside the unit circle. And then because this is a complex, now we need to have its conjugate, which will be here. And again, I can express x of n here to be 2, 1.2n cosine pi over 4n. Same oscillation as this one, but here it's larger than 1, so the sinusoidal will increase with time or with n. Now, if the magnitude here is 1, that means on the unit circle, then it will be exactly the same as this case, except this will be 1 to the power of n cosine pi over 4n. So 1 to the power of n is just 1, so this will just keep oscillating forever. Now, the difference between this signal here and this signal here is in omega. Now here omega is 3 pi over 4. So x of n here will be 2 cosine 3 pi over 4n. Now if I express this omega in this form, 2 pi 3 over 8. Now these tell me there are 3 cycles per 8 samples, where these tell me, let me write it in this form, 1 cycle per 8 sample. So the difference between this one and this one is just the oscillation rate. Here it's higher. 3 cycles per 8 samples. 3 pi over 4, that will be this one here. That's omega. Okay, so this z, we will relate it to the Z transform and x of n. So basically, any signal in the time domain, x of n, can be represented as a linear sum of these z variables of specific magnitude and specific frequency. Now let's try to visualize the signal in the time domain and the z domain. So here we have a signal in the time domain. I can tell a little bit about the signal in the time domain. It just fluctuates between positive values and negative values. Now, if I need to know what are the frequency content of this signal, I won't be able to tell from the time domain. But if I do the Z transform, I will discover the following. This signal here will have a Z component 0.8. So 0.8, let's say it is here. So the length is 0.8 and omega is 0. Omega is the frequency between the x-axis and the vector. That's what we call omega. So in this case, so for this 0.8, omega is 0. So that tells me this signal here will have this component, 0.8 to the power of n. And the magnitude of it will be represented by this axis. So that will be somewhere like this. So that length is 0.5, which is this here. It will also tell me the Z transform, it has a component minus 0.7. So that is somewhere maybe here. And the strength of it is minus 0.4. So that will be this Z. So if I call this Z1, this will be Z2. And the strength is it minus 0.4. Also, the Z transform will tell me that this signal has this frequency, 0.8 pi over 4. The length here 0.8 and this is pi over 4. And that will be this Z. And the strength of it will be 2 plus J3. That will have a magnitude and also a phase. So the magnitude will be this length will be the magnitude of 2 plus J3, and it also has an angle. So if I draw this one, it will probably look something decay and there is some phase shift, and the magnitude here, it will tell me where does it start, here or here. So it will be something like this. Since this is a complex, we have to have its conjugate, which is this one. So that will be somewhere here. And minus J pi over 4, that will be here. And again, this harmonic will have this magnitude, let's call this the magnitude of Z, and an angle. And another component, 1 plus Ej pi over 2. If this is the unit circle, so that will be here. And it has also the conjugate here. And the length is 1. And the strength of this harmonic will be the magnitude of this, and it will be phase shifted by this. So that it will have a magnitude, which is the magnitude of this complex, and it will have a phase. Let me clean up. So by carrying out the Z transform of this signal, it first told me what are the frequency components. These are DC. This has frequency components. And the Z transform told me the magnitude of each one of them, which is this blue. That's basically the link between the Z transform and x of n. Now this signal x of n is in the time domain. If I plot this equation, I will get exactly this plot. Now that we visualize the relationship between the signal in the time domain and the signal in the Z domain, let's find what is the mathematical expression that convert a signal in the time domain x of n to a signal in the Z domain x of z. First, the bilateral Z transform means x of n will have value for positive and negative n. When we say unilateral signal, that means x of n will have only values for positive n. So a signal will exist only in this time domain. So the Z transform is a mathematical tool in system analysis and design. It represents input signal x of n as a sum of everlasting exponentials of the form Zn. Everlasting exponential, these functions. A sum of linear combination of these of different amplitude and phase shift. Now, if I have the signal in the time domain x of n, and I want to know what are the frequency content or what's x of z. So I will multiply x of n by z of different values, different magnitude and different digital frequency omega. And after I multiply sample by sample, I do the sum. And if the sum is large, that means this component is present in this signal. This component can be, for example, 0.8 Ej pi over 3n. So I multiply this signal times x of n. sample by sample, then I sum, and the sum will tell me how much of this signal present here. And that sum will be usually complex, and that will be x of z naught, if I call this z naught. Then I do this again for another z, multiply, sum, and then it will give me a magnitude. If I have something like this, 1.3 ej pi over 10, and I multiply it times x of n and I get 0, that means this signal is not present in x of n. And if it's bilateral, that means the signal x of n exists for negative n and positive n. Now there is a very close relationship between the Z transform and the Laplace transform. Laplace is for a continuous signal x of t, Z for a discrete signal. Here, the everlasting signal is e minus s of t, which is continuous, and here it is a discrete. So I can think of Z as e minus sigma plus j omega, where this is s. So then it will be e minus sigma, e minus j omega. And t here will be n times the sampling interval. And integration is for continuous signal, for discrete is a summation. And that's the relationship between x of z, the Z transform, and x of s, the Laplace transform. And as I said before, that z, everlasting signal, it has r, which is this one, and a frequency, which is omega. And the relationship between the digital frequency omega and the analog frequency is this one. So you multiply omega by the sampling interval, or it's the same as omega over fs, where fs is the sampling rate. So that is 2 pi f over fs. Now, because f of s, the sampling rate, is twice the highest frequency in the signal, this always gonna be less than half. So half times 2 pi, that means omega will be always less than pi. The 2 will cancel here and you have pi. And that's the digital frequency. For sampling with no aliasing, the digital frequency omega is from 0 to pi, which is here, from 0 to pi. This is all possible. Omega. Now, to do the inverse Z transform, so now I have the signal in the Z domain and I need to get x of n. So I carry out this integral, which we will not do in undergraduate course because these involve complex variable theory, which we learn it usually in graduate study. But how do we find the inverse Z transform? We will do the partial fraction expansion. So I may have x of z that looks like z squared plus 3z over z cubed plus 2z squared. So then I do partial fraction expansion, and then I use the table to find the inverse Z transform. And this is the notation we will be using in the lecture. That's x of n, Z transform, I get x of z. So let's take an example to demonstrate how do we calculate this summation. Find the Z transform and the corresponding region of convergence for this signal. X of n is gamma n u of n. Let's follow the definition. X of z. And if I plug the value for x of n, that will be n minus infinity to infinity. Now, u of n is a unit step function that exists only for positive n. So that will determine this limit. So this limit will start from n equals 0 to infinity. And in this interval from 0 to infinity, it's just 1. So this is just equal 1. So I don't need to write it. So this will be just gamma n z minus n. Now to carry out this summation, we will be using the summing formula, which is this one. So to make my term here looks like r to the power of n, I will do the following. Z minus n is the same as 1 over z to the power of n. So this will be just gamma over z to the power of n. Now this is my r. If I compare it to this is my p, and infinity is m. So the answer will be r to the power of p. So that is gamma divided by z to the power of p, which is 0, minus r gamma over z to the power of m plus 1, which is infinity plus 1, over 1 minus r. And anything to the power of 0 is just 1. Anything to the power of infinity, it could go either to infinity or to 0. If it goes to infinity, then z doesn't exist. So for x of z to exist, this quantity here has to be less than 1. So this would be minus 0 for gamma over z, that is the magnitude less than 1. 1 minus gamma over z. And if I clean up this, I will just multiply numerator and denominator by z, and I will have this z over z minus gamma. And this basically is same as gamma less than z, or z larger than the magnitude of gamma. Z larger than the magnitude of gamma. So for this signal, the Z transform is this. And the region of convergence, all value of z with magnitude or the vector length is larger than gamma. So if gamma, let's say 0.8, so I draw it here, then I draw a circle with radius 0.8 or gamma. And the region of convergence, all value of z outside this circle. So this signal here has all these frequency components. Now, if I plot the magnitude x of z, the magnitude, it will be a surface plane in top of this horizontal plane that is shaded. If gamma was 0.8. So that will be here. So if I plot this x of z, it will be a surface with a peak in top of this 0.8 point. Then it starts decay. So if I plot it like something like this, and this is 0.8, and this is the circle. So at 0.8, it will have a very high amplitude, and the surface plane will start decaying at other frequencies. Okay, let's take another example just to show you the importance of the region of convergence. Let's clean up. Let's define y of n here to be gamma to the power of n, but it is anti-causal. That means it only exists for negative value of n. For positive n, it's 0. For negative n, it has values. And this plot will depend on the value of this gamma. And I need to find the region of convergence. So let's clean up and start solving this problem. Okay, the definition of the Z transform. If I plug value for x of n, then it will be. Now, if I plot this u, the unit step function, it will look something like this. It has only value for minus 1, minus 2, minus 3, minus 4, all the way to minus infinity, and 0 here. So then this will determine the summation limit. So it starts from n minus infinity to minus 1, because it exists up to minus 1. And this unit step function will have value 1. So I don't need to write it. So that will be minus gamma n z minus n. Again, z minus n is the same as 1 over z to the power of n. So I can rewrite the summation as n minus 1. I bring the minus outside the summation. And this is gamma over z n. And if I use this, it will be exactly the same one we did in this example. The minus will be here. R in this case is gamma over z. P in this case is minus infinity minus r, which is gamma over z to the power of m plus 1. M here is minus 1. So minus 1 plus 1, that's 0. 1 minus r. And this is equal. Minus. Now, this we have no problem with. Anything to the power of 0 is just 1. So that would be minus 1. But this one, since it is to the power of negative infinity, then gamma over z has to be larger than 1. Because remember, 2 to the minus 1 will be 1 over 2. So that's less than 1. So this will decay as n goes to minus infinity if gamma over z is larger than 1. So that means this will be true for gamma over z larger than 1. Divided by 1 minus gamma over z. The minus here will cancel this minus, so I have 1. 1 minus gamma over z. Multiply numerator and denominator by z, I get z over z minus gamma. And here, the region of convergence, gamma is larger than Z, or Z is less than gamma. And gamma, because it can be complex, then we just take the magnitude. So if I draw this region, then I plot a vector of gamma length and plot a circle, and any Z value in this region inside this circle will have a magnitude less than gamma. So this is the region of convergence. And that's Y of Z. Exactly the same to this X of Z here, except the region of convergence is different. So for a causal signal, that means a signal that exists for positive n, the region of convergence is outward of the circle determined by the vector gamma. And if the signal is anti-causal, that means the signal exists for negative n, then the region of convergence is inward to the centered circle, to this circle. And this circle determined by, again, gamma. So remember, causal signal, region of convergence, outward, anti-causal, inward. Now let's take another example where you may have signal that is causal and anti-causal. So how do we deal with this? So we have a signal, omega n, that consists of x of n and y of n. And x of n is defined by this, that's causal, and y of n is anti-causal. And we need to know what is omega z. So we haven't talked about property of the Z transform, but Z transform is linear operation. That means omega of z equal x of z plus y of z. And if we try to find x of z for this signal here, we follow the same step. And this will be r to the power of 0 minus r to the power of infinity plus 1 minus r. This will be 1 over 1 minus 0.9 over z, and region of convergence, this has to be, since this is to the power of infinity, less than 1, or z is larger than 0.9. So for this x of z, multiply numerator and denominator by z, you will get this one, z over z minus 0.9 for z larger than 0.9, the magnitude. And if we plot it, then the region of convergence will be all these outward, and that here 0.9. And same thing now, if we calculate y of z for this one, for region of convergence, for this to be 0, 1.2 over z has to be larger than 1, and 1.2 larger than z, or z less than 1.2. And we can simplify these further by multiplying numerator and denominator by z, so that would be minus z minus 1.2, and region of convergence, the magnitude of z is less than 1.2. If I plot the region of convergence here, this is a circle of 1.2, and it has to be the magnitude less, so it is in this region. So w of z, then it will be x of z that we found it to be here, and y of z, which is this one. And the region of convergence for this one is larger than 0.9, for this one is less than 1.2. So the common region between the two will be this. So if this is, it has to be larger than 0.9 for the causal signal, and for the anti-causal it has to be less than 1.2. So the common region for both will be this shaded one. I will leave it to you to try by changing x of n to 2 to the power of n. For this case, the region of convergence will be larger than 2. And this one, for omega n, we said it's less than 1.2, which is here. So there is no common region of convergence for x of 1, this one, and y of n, which is this one. So then w of z doesn't exist. Let's clean up. Let's do this example. But before we do it, as we said before, if the signal x of n equals 0 for n less than 0, that means it's a causal signal, then the Z transform is unilateral. That means it starts from n equals 0 to infinity. Okay, so this example, part A, find the Z transform of this impulse. So if I plot x of an, it's just an impulse at n equals 0. So even though it's in the time domain a simple signal, but because at n negative it's 0, 0, then suddenly jump to an impulse, then go back to 0, this sudden change means it has a lot of frequency content. So we expect the spectrum of this impulse in the Z transform will have many, many values. So let's carry out the definition. X of az equal. Now this x of n here, it only equal 1 at n equals 0. So then this will be, and it is the impulse of delta n, and this is just 1, because this is 1 at n equals 0, 0 everywhere else. Now the region of convergence, all the z plane. This will always equal 1 regardless of the value of z. Let's take this example. If I plot xb of n, it's u of n minus u of n minus 5. So it will start here and keep going 1 all the way to n equal 4. And this is 1. So then for xp of z, it will be from n equals 0 to n equal 4, xb of n, z minus n. Now this function equal 1 in this range. So this will be n equals 0 to 4, 1 z minus n. And if I use this definition, then in this case, it will be, and here r is 1 over z. So this will be 1 over z to the power of 0 minus 1 over z to the power of 4 plus 1, that's 5, divided by 1 minus r, which is 1 over z. And I can simplify this, 1 minus z minus 5 over 1 minus 1 over z. Now I can multiply numerator and denominator by z just to get rid of this 1 over z. So this will be z minus over z minus 1. And I can simplify this further as z over z minus 1 minus z over z minus 1, z minus 5. Now what's the region of convergence? Well, for this summation to exist, z can be anything except here. Z cannot be 0 because 1 over 0 is infinity. So the region of convergence everywhere except at z equals 0. Now this one here is the Z transform of u of n. This one here with this is the Z transform of u of n minus 5, this part. And later on when we do the property, this is a delayed version of this one by 5 units. So a delay in the discrete time means z minus 5 in the Z transform. So the same thing, except now this one, because it's delayed 5 units, you multiply it by z minus 5. Now, existence of the bilateral Z transform. This is the definition of the Z transform. As long as this quantity does not go to infinity, then there is a Z transform for the signal x of n. X of n, it can be anything as long as it doesn't grow faster than this rate, r of n. Why? Because in this definition, we will divide always r over z to the power of n. And as long as z larger than r, this summation will exist. But if x of n grow faster than this one, then no matter what is z, it can never make this less than 1. For example, r n squared. There is no z transform for this function. Now, in real life, most signals will be like finite, and it could be either for positive n and also could be for negative and positive n. For finite length sequence, the region of convergence is the entire z-plane except 0. If x of n is non-zero for some positive n. That means if x of n has some value here, then when you do the z transform, it will be divided this value x of n by z. So then z cannot be 0. Otherwise, this quantity will go to infinity. And if x of n is non-zero for some negative n, that means if there are samples for negative n here, then infinity cannot be part of the region of convergence. Because, again, when we carry out the z transform definition, it will be x of n divided by z n. Now for negative n, this is the same as z over x of n. When n is negative 2, same as 2. So if this is like negative 2, this will be the same. Now z cannot go to infinity. So that's not part of the region of convergence because this will go to infinity. If I have a function that consists of two different functions, then the region of convergence of z has to be the common region where x and y converge. For example, if this is the region of convergence for x, and this is the region of convergence for y, then the region of convergence for this function will be this common region between the two. Okay, this table contain popular functions and their z transforms. You can use these tables for homework unless if you were asked to find the z transform using the definition. We did this one, this one, this one, this one, and these are other popular functions. And this is for anti-causal signal with z transform and region of convergence. This ends this video, and next video we will talk about the inverse z transform. That means now if I have x of z and it looks like this, how can I find the inverse z transform to find x of n? Thank you for watching and see you next video.